Although I'm not going to do the proof that SST is equal to SSW plus SSB, I do want you to see both. This is kind of neat, right? Because each of these quantities is calculated by a sum of 6 different squared quantities after this example where n equals 6. And we could see how to derive each of the quantities, but it happens that they add up to each other. But also that intuitively, we're saying that the overall variance can be decomposed into the variance within each group plus the variance between each group. I want to say one more thing about this SSB quantity. When we talked about SST, we said, hey, this relates to something else we already know. And it turned out that SST is the numerator of the sample variance. When we talked about SSW, we said, hey, this relates to something else we already know. And it turned out that SSW was the numerator of the pooled sample variance. What about SSB? It's a little bit less straightforward for SSB, but just like SST and SSW, SSB can be related intuitively to a particular quantity. So we're going to try to do that. The thing is, in order to do this, we have to make an assumption, a slight simplifying assumption. If the sample size is the same in each of the groups, as it was in our little example with six data points, 3 from each group. So if that's true, then you could take your total sample size and divide it by the number of groups, and you get some number. Let's call it N1, right? And then that'll be the sample size in each group. So, for example, we had 6 data points in 2 groups, and so there were 3 in each group, right? Crucially, this is not a requirement for this method or for this test or for this sum of square decomposition. Just a simplification so that you can see the intuition on the slide. Just a simplification to show the intuition. If we assume the sample sizes are the same in every group, then think about what the SSB quantity was. Well, it was, in the case of this little example, 12 minus 8 squared plus 12 minus 8 squared plus 12 minus 8 squared plus 4 minus 8 squared plus 4 minus 8 squared plus 4 minus 8 squared. For each data point, we took the mean in its own group minus overall mean. And that implies that for every data point from the same group, actually that squared quantity is the same number, right? So another way to say that would be, well, it's going to be the group 1 mean minus the overall mean squared. So that's equivalent to the 12 minus 8 squared times the number of data points in the first group, plus number of data points in the second group, which is also n minus 1, we're assuming. And that's how many times we're going to write down the group 2 mean minus the overall mean. I'm purposely using words here instead of notations. I think it's easier in this case. So essentially what I'm saying is that instead of writing 12 minus 8 squared plus 12 minus 8 squared plus 12 minus 8 squared plus 4 minus 8 squared plus 4 minus 8 squared plus 4 minus 8 squared, we could have written 3 times 12 minus 8 squared plus 3 times 4 minus 8 squared. That's all I'm saying. But then note, well, of course, you can pull out the N1 here, okay? And then what we have is each of the group means minus the overall mean squared, add them up. That sounds like the numerator of a variance, right? What variance? Well, in particular, if we took each of the within group means, like 12 and 8, and pretended those numbers were our data set, we could calculate their variance. Okay, so the sample variance of the group sample means. Well, and in particular, I'm not done with this equation yet. The sample variance of the group sample means should be, well, the first group mean minus the overall mean squared plus the second group mean minus the overall mean squared divided by number of group means minus 1. So to make this equation work, I then have to multiply by that number at the end here. number of group means minus 1. Okay, so why are we doing this? Well, just like SST can be written as a function of S squared, just like SSW can be written as a function of SP squared, SSB can be written as a function of the sample variance of each of the sample means. So SST reflects the overall variance, and that's why it reflects the S squared, which is just the overall variance. SSW reflects the variance within each group, which is why it's a function of SP squared, the estimate of the variance within each group. SSB reflects how far the group means are from each other, which is why it's a function of the variance of the sample means, if you were to take that variance. Note that this assumption we made, that the sample size is the same in each group, is useful for this intuition. Like we can't pull out the N1 the way we did here. So if we don't have sample size the same in each group, we can't literally write down SSB as a function of the sample variance of the group sample means. However, if the sample sizes are different in each group, the intuition is still there, that SSB is reflecting the squared differences between each group mean and the overall mean. So what do we do with all this, right? Remember, the whole point here is to come up with a test statistic. So could you pause and say, well, my goal was to see how much bigger SST was than SSW, so I just want to see how big SSB is? Yes, you could do that, okay? Just using SSB as your test statistic would make some sense. You could do that. Turns out it's a particular version, a particular function of SSB that we typically use. Just like with a t-test, could we just use the difference in sample means as a test statistic? You could, right? But there's a convention for the particular test statistic we use. And the reason we use the t-statistic that we usually do is because we can show that it follows a t-distribution, and then we know what to use as a reference distribution to get a p-value. Similarly here, when we do what's called the extra sum of squares f-test, we're not just going to use SSB as our test statistic. We're going to use a particular function of SSB because it happens to be true that we know what the distribution of that statistic should be when the null hypothesis is true, and therefore we know how to get a p-value. This is a parametric test because it involves parameters. We're estimating means. The null hypothesis, as we've been saying all along, is that the mean is the same in each group. So we can write that like this: mu1, which is the mean of the first group, is the same as mu2, which is the mean of the second group, et cetera, all the way to mu I, which is the mean in the last group. And so then the alternative is that at least one population mean is different from the others. The assumptions you need are exactly a generalization of the pooled t-test. So you need normality within each group. You need independence within the group, so independent sampling within each group and between. So the fact that a particular data point is drawn for group A doesn't tell me anything about whether a particular data point will be included in group B. And you need equal variance, just like with the pooled t-test. Let's mention robustness, since we've talked about that before. But just like with the t-test, this extra sum of squares f-test is fairly robust to normality, but the independence assumption is crucial. And the equal variance assumption is not crucial if the sample sizes are all equal. But if the sample sizes are not all equal, then we do need to worry more about equal variance. Not crucial if equal sample sizes. So what is this f-test? This is test statistic we've been working toward. So shockingly, it's called an F. What is it? It's SSB divided by I minus 1, number of groups minus 1, whole thing over SSW divided by n minus I. Here is the test statistic that we've been working toward. Here's the conventional test statistic. So let's try to get some intuition for it. When is this quantity big? Well, it's big when its numerator is big. So F will be big when SSB is big. What is SSB? It reflects the variance of the within group sample means. Hey, that was one of the two things that we hoped our test statistic would do. If the sample means are very far apart, then that is evidence against the null hypothesis. So F is a statistic that is bigger when SSB is big. It's bigger when the sample means in the different groups are further apart. Okay. What else is F big? S is big. Well, it's big when its numerator is big. It's also big when its denominator is small. Right? So F is big when SSW is small. Right? Look at that fraction. If SSW is small, that makes F bigger. Well, SSW is the variance within each group. Hey, that was the other one of the two things we hoped our test statistic would reflect. We said that when the variance within each group is small, that makes the population means seem like they might be more different from each other because the pattern of sample means we observe seems less likely to occur due to chance. So now we see that we have managed to construct a test statistic that is big when the sample means are very different from each other and small when the sample means are close to each other. It's big when the variances within each group are small and small when the variances within each group are big. And of course, for any particular data set, the sample means will be a certain distance apart and the sample variances within each group will be certain quantities. And this statistic F weighs those together. In subsequent videos, you'll see how we can set up the information that I've shown you here in something called an ANOVA table, and also how you can use this test statistic to generate a p-value. The last thing I want to mention before closing here is just how you do this in R. So note, first of all, that whatever your grouping variable is has to be a factor in order for R to be willing to do this test. So let's say our group variable was called group. We want to make a new one called group 1, which is just as.factor of our grouping variable. In other words, if your grouping variable is currently numeric or a character, this isn't going to work, has to be a factor. You should always make a picture before you do any test, including an extra sum of squares F test. So if Y is my outcome variable and G is my grouping variable, that's a factor. That is how I'll make my box plot. And the way you want to do the extra sum of squares F test is to say out, it's your output, and then AOV, which stands for analysis of variance, Y tilde group. So don't Google how to run an F test. You'll find various things. There's more than one kind of F test. What I'm asking you to do, if I ask you to do an extra sum of squares F test, is use AOV. And then to see the results, you say summary, parentheses, out.